Alternating current. Introduction. We have so far considered direct current, DC, sources and circuits with DC sources. These currents do not change direction with time, but voltages and currents that vary with time are very common. The electric mains supply in our homes and offices is a voltage that varies like a sine function with time. Such a voltage is called alternating voltage, AC voltage, and the current driven by it in a circuit is called the alternating current, AC current. Today, most of the electrical devices we use require AC voltage. This is mainly because most of the electrical energy sold by power companies is transmitted and distributed as alternating current. The main reason for preferring use of AC voltage over DC voltage is that AC voltages can be easily and efficiently converted from one voltage to the other by means of transformers. Further, electrical energy can also be transmitted economically over long distances. AC circuits exhibit characteristics which are exploited in many devices of daily use. For example, whenever we tune our radio to a favorite station, we are taking advantage of a special property of AC circuits, one of many that you will study in this chapter.
AC voltage applied to a resistor. Figure 7.1 shows a resistor connected to a source epsilon of AC voltage. An AC source in a circuit diagram is as shown in the symbol. We consider a source which produces sinusoidally varying potential difference across its terminals. Let this potential difference, also called AC voltage, is given by the equation 7.1, that is V is equal to Vm sin omega t, where Vm is the amplitude of the oscillating potential difference and omega is its angular frequency. To find the value of current through the resistor, we apply Kirchhoff's loop rule, summation epsilon t equal to 0, to the circuit shown in figure 7.1 to get Vm sin omega t equal to IR, or I is given by Vm by R sin omega t. Since R is a constant, we can write this equation as I equal to Im sin omega t, where the current amplitude Im is given by Im is equal to Vm by R. Equation 7.3 is called Ohm's law, which for resistors works equally well for both AC and DC voltages. The voltage across a pure resistor and the current through it, given by the equation 7.1 and 7.2, are plotted as a function of time in this figure 7.2. Note in particular that both V and I reach zero minimum and maximum values at the same time. Really, the voltage and current are in phase with each other. You see that, like the applied voltage, the current varies sinusoidally and has corresponding positive and negative values during each cycle. Thus, the sum of the instantaneous current values over one complete cycle is 0 and the average current is also 0. The fact that the average current is 0, however, does not mean that the average power consumed is 0 and that there is no dissipation of electrical energy. As you know, Joule heating is given by I square R and depends on I square, which is always positive, whether I is positive or negative, or not on I. Thus, there is Joule heating and dissipation of electrical energy when an AC current passes through a resistor. The instantaneous power dissipated in the resistor is given by P equal to I square R, and that's equal to Im square R sin square omega t. The average value of P over a cycle is given by P equal to I square R, and that's equal to Im square R sin square omega t, where the bar over the letter denotes its average value and the bracket denotes taking average of the quantity inside the bracket. Since Im square and R are constants, P is given by Im square R sin square omega t. Using the trigonometric identity, sin square omega t is given by half into 1 minus cos 2 omega t. So we have sin square omega t equal to half 1 minus cos 2 omega t. And since cos 2 omega t equal to 0, we will have sin square omega t equal to half. Thus, P is given by half Im square R. To express AC power in the same form as DC power, P equal to I square R, a special value of current is defined and used. And that is called as root mean square or effective current, and that is denoted by IRMS or I. It is defined by I equal to root of I square bar, and that's equal to root of half Im square, and that's given by Im by root 2, and that value is given by 0.707 into Im. In terms of I, the average power denoted by P is given by P equal to P bar, that's equal to half Im square R, and that's given by I square R. Similarly, we define the RMS voltage or effective voltage by V equal to V maximum by root 2, and that's equal to 0.707 means Vm. From the equation 7.3, we have Vm equal to IMR, or Vm by root 2 equal to Im by root 2 into R, and that's given by V equal to IR, that is Ohm's law. Equation 7.9 gives the relation between alternating current and alternating voltage, and is similar to that in the DC case, that is in the direct current case. This shows the advantage of introducing the concept of RMS values. In terms of RMS values, the equation for power, that is equation 7.7, and the relation between current and voltage in AC circuits are essentially the same as those for the DC case. It is customary to measure and specify RMS values for AC quantities. For example, the household line voltage of 220 volts is an RMS value with a peak voltage of Vm equal to root 2 times V, just given by 1.414 into 220 volts, that is equal to 311 volts. In fact, the I or RMS current is the equivalent DC current that would produce the same average power loss as the alternating current. The equation 7.7 can also be written as P is equal to V square by R, that's equal to IV, since V is equal to IR.
Representation of AC current and voltage by rotating vectors, phases. In the previous section, we learnt that the current through a resistor is in phase with the AC voltage. But this is not so in the case of an inductor, a capacitor, or a combination of these circuit elements. In order to show phase relationship between voltage and current in an AC circuit, we use the notion of phases. The analysis of an AC circuit is facilitated by the use of a phasor diagram. A phasor is a vector which rotates about the origin with angular speed omega as shown in figure 7.4. The vertical components of phasors V and I represent the sinusoidally varying quantities V and I. The magnitudes of phasors V and I represent the amplitudes or the peak values Vm and Im of these oscillating quantities. Figure 7.4 shows the voltage and current phasors and their relationship at time t for the case of an AC source connected to a resistor, i.e., corresponding to the circuit shown in figure 7.1. The projection of voltage and current phasors on vertical axis, that is Vm sin omega t and Im sin omega t respectively, represent the value of voltage and current at that instant. As they rotate with frequency omega, curves in figure 7.4b are generated. From figure 7.4 we see that phasors V and I for the case of a resistor are in the same direction. This is so for all times. This means that the phase angle between the voltage and the current is zero. AC voltage applied to an inductor. Figure 7.5 shows an AC source connected to an inductor. Usually, inductors have appreciable resistance in their windings, but we shall assume that this inductor has negligible resistance. Thus, the circuit is a purely inductive AC circuit. Let the voltage across the source be V equals V sin omega t. Using the Kirchhoff's loop rule, summation epsilon t equal to 0, and since there is no resistor in the circuit, we get the equation 7.10, where the second term is the self-induced Faraday EMF in the inductor, and L is the self-inductance of
the inductor. The negative sign follows from Lenz's law given in chapter 6. Combining the equations 7.1 and 7.10, we have di by dt equal to v by L, that's given by Vm by L sin omega t. The equation 7.11 implies that the equation for it, the current as a function of time, must be such that its slope di by dt is a sinusoidally varying quantity with the same phase as the source voltage and an amplitude given by Vm by L. To obtain the current, we integrate di by dt with respect to time. So integral di by dt into dt, that's equal to Vm by L integral of sin omega t dt. And we get I is equal to minus Vm by omega L into cos omega t plus constant. The integration constant has the dimension of current and is time independent. Since the source has an EMF which oscillates symmetrically about zero, the current it sustains also oscillates symmetrically about zero, so that no constant or time independent component of the current exists. Therefore, the integration constant is zero. Using minus cos omega t equal to sine of omega t minus pi by 2, we have I is equal to Im sine omega t minus pi by 2, where Im is equal to Vm by omega L is the amplitude of the current, that is the maximum value of current. The quantity omega L is analogous to the resistance and is called inductive reactance, and that is denoted by the letter XL. So XL is given by omega L, and the amplitude of the current is given by Im equal to Vm by XL, where this Vm is the maximum value of the voltage. The dimension of inductive reactance is the same as that of resistance and its SI unit is ohm, given by the symbol omega. The inductive reactance limits the current in a purely inductive circuit in the same way as the resistance limits the current in a purely resistive circuit. The inductive reactance is directly proportional to the inductance and to the frequency of the current. A comparison of the equation 7.1 and 7.2 for the source voltage and the current in an inductor shows that the current lags the voltage by pi by 2 or 1/4 cycle. And the figure 7.6a shows the voltage and the current phasors in the present case at instant t1. The current phasor I is pi by 2 behind the voltage phasor v. When rotated with the frequency omega counterclockwise, they generate the voltage and current given by the equation 7.1 and 7.12 respectively and as shown in figure 7.6b. We see that the current reaches its maximum value later than the voltage by 1/4 of the period, that is given by t by 4 equal to pi by 2 by omega. You have seen that an inductor has a reactance that limits current similar to resistance in a DC circuit. Does it also consume power like a resistance? Let us try to find out. The instantaneous power supplied to the inductor is given by PL equal to IV, and that's given by Im sine of omega t minus pi by 2 into Vm sine omega t. That's given by minus Im Vm cos omega t sine omega t. That's given by minus Im Vm by 2 into sine 2 omega t. So the average power over a complete cycle is given by PL equal to minus Im Vm by 2 into sine 2 omega t. That's given by minus Im Vm by 2 into sine 2 omega t, that's equal to 0. Since the average of sine 2 omega t over a complete cycle is 0, thus the average power supplied to an inductor over one complete cycle is 0. AC voltage applied to a capacitor. Figure 7.7 shows an AC source epsilon generating AC voltage V equal to Vm sin omega t connected to a capacitor only, a purely capacitive AC circuit. When a capacitor is connected to a voltage source in a DC circuit, current will flow for the short time required to charge the capacitor. As charge accumulates on the capacitor plates, the voltage across them increases, opposing the current. That is, the capacitor in a DC circuit will limit or oppose the current as it charges. When the capacitor is fully charged, the current in the circuit falls to zero. When the capacitor is connected to an AC source, it limits or regulates the current but does not completely prevent the flow of charge. The capacitor is alternately charged and discharged as the current reverses each half cycle. Now, let Q be the charge on the capacitor at any time t. The instantaneous voltage V across the capacitor is given by V equal to Q by C. From the Kirchhoff's loop rule, the voltage across the source and the capacitor are equal. So, Vm sin omega t is equal to Q by C. To find the current, we use the relation I equal to dq by dt, and I is equal to d by dt of Vm C sin omega t. This is for Q, the charge, and that's given by omega C Vm cos omega t. By using the relation cos omega t equal to sin omega t plus pi by 2, we will obtain the equation I is equal to Im sin omega t plus pi by 2, where the amplitude of the oscillating current is given by Im and thus equal to omega C Vm. We can rewrite this equation as Im is equal to Vm by 1 by omega C. Comparing it to Im equal to Vm by R for a purely resistive circuit, we find that 1 by omega C plays the role of resistance. So it is called as capacitive reactance and is denoted by letter Xc. So Xc is given by 1 by omega C, so that the amplitude of the current is given by Im equal to Vm by Xc. The dimension of capacitive reactance is the same as that of resistance and its SI unit is ohm. The capacitive reactance limits the amplitude of the current in a purely capacitive circuit in the same way as the resistance limits the current in a purely resistive circuit, but it is inversely proportional to the frequency and the capacitance. A comparison of the equation 7.16 with the equation of source voltage equation 7.1 shows that the current is pi by 2 ahead of voltage. The figure 7.8a shows the phasor diagram at an instant t1. Here, the current phasor I is pi by 2 ahead of the voltage phasor V as they rotate counterclockwise. Figure 7.8b shows the variation of voltage and current with time. We see that the current reaches its maximum value earlier than the voltage by 1/4 of a period. The instantaneous power supplied to the capacitor is given by Pc equal to IV and thus equal to Im cos omega t Vm sin omega t, and that is given by Im Vm into cos omega t sin omega t, and that is given by Im Vm by 2 into sin 2 omega t. So as in the case of an inductor, the average power is given by Pc equal to Im Vm by 2 into sin 2 omega t, and that's equal to Im Vm by 2 into sin 2 omega t, that's equal to 0, since sin 2 omega t equal to 0 over a complete cycle. Thus, we see that in the case of an inductor, the current lags the voltage by pi by 2, and in the case of a capacitor, the current leads the voltage by pi by 2.
AC voltage applied to a series LCR circuit. Figure 7.10 shows a series LCR circuit connected to an AC source epsilon. As usual, we take the voltage of the source to be V equals Vm sin omega t. If Q is the charge on the capacitor and I the current at time t, we have, from Kirchhoff's loop rule we get the equation 7.20. We want to determine the instantaneous current I and its phase relationship to the applied alternating voltage versus. We shall solve this problem by two methods. First, we use the technique of phases, and in the second method, we solve equation 7.20 analytically to obtain the time dependence of I.
Phasor diagram solution. From the circuit shown in figure 7.10, we see that the resistor, inductor and capacitor are in series. Therefore, the AC current in each element is the same at any time, having the same amplitude and phase. Let it be I equal to Im sin omega t plus pi, where pi is the phase difference between the voltage across the source and the current in the circuit. On the basis of what we have learned in the previous sections, we shall construct a phasor diagram for the present case. Let I be the phasor representing the current in the circuit as given by the equation 7.21. Further, let VL, VR and VC and V represent the voltage across the inductor, resistor, capacitor and the source respectively. From the previous section, we know that VR is parallel to I, VC is pi by 2 and behind I, and VL is pi by 2 ahead of I. So VL, VR, VC and I are shown in figure 7.11a with appropriate phase relations. The length of these phasors or the amplitude of VR, VC and VL are given by the equations VRM equal to IM or VCM equal to IM XC and VLM equal to IM XL, where this R is the resistance, XC is the inductive reactance and XC is the capacitive reactance and XL is the inductive reactance. So the voltage equation 7.20 for the circuit can be written as VL plus VR plus VC equal to V. If there is a relation whose vertical component gives the above equation is VL plus VR plus VC equal to V. So this relation is represented in figure 7.11b. Since VC and VL are always along the same line and in opposite directions, they can be combined into a single phasor VC plus VL which has a magnitude VCM into VLM. Since V is represented as a hypotenuse of a right angle triangle whose sides are VR and VC plus VL, the Pythagorean theorem gives VM square equal to VRM square plus VCM minus VLM the whole square. Substituting the values of VRM, VCM and VLM from the equation 7.22 into the above equation, we get Vm square equal to Im into R whole square plus IMXC minus IMXL the whole square. That's given by Im square into R square plus Xc minus XL the whole square. Im can be written as Vm by root of R square plus Xc minus XL the whole square. By analogy to the resistance in a circuit, we introduce the term impedance Z in an AC circuit. That is given by Im equal to Vm by Z, where Z, that is called as the impedance, the circuit, is given by a root of R square plus Xc minus XL the whole square, where this Xc is the capacitive reactance and XL is the inductive reactance.
Since phasor I is always parallel to phasor V, the phase angle phi is the angle between VR and V and can be determined from figure 7.12. Tan phi equals VCM minus VLM by VRM. Using equation 7.22, we have tan phi equals XC minus XL by R. Equations 7.26 and 7.27 are graphically shown in figure 7.12. This is called impedance diagram, which is a right triangle with Z as its hypotenuse. Equation 7.25 gives the amplitude of the current and equation 7.27 gives the phase angle. With these, equation 7.21 is completely specified. If XC is greater than XL, phi is positive and the circuit is predominantly capacitive. Consequently, the current in the circuit leads the source voltage. If XC is less than XL, phi is negative and the circuit is predominantly inductive. Consequently, the current in the circuit lags the source voltage. Figure 7.13 shows the phasor diagram and variation of V and I with omega t for the case XC greater than XL. Thus, we have obtained the amplitude and phase of current for an LCR series circuit using the technique of phasors. But this method of analyzing AC circuits suffers from certain disadvantages. First, the phasor diagrams say nothing about the initial condition. One can take any arbitrary value of t, say, t1, and draw different phases which show the relative angle between different phases. The solution so obtained is called the steady-state solution. This is not a general solution. Additionally, we do have a transient solution which exists even for versus equals 0. The general solution is the sum of the transient solution and the steady-state solution. After a sufficiently long time, the effects of the transient solution die out and the behavior of the circuit is described by the steady-state solution. Resonance. An interesting characteristic of the series RLC circuit is the phenomenon of resonance. The phenomenon of resonance is common among systems that have a tendency to oscillate at a particular frequency. This frequency is called the system's natural frequency. If such a system is driven by an energy source at a frequency that is near the natural frequency, the amplitude of oscillation is found to be large. A familiar example of this phenomenon is a child on a swing. The swing has a natural frequency for swinging back and forth like a pendulum. If the child pulls on the rope at regular intervals and the frequency of the pulls is almost the same as the frequency of swinging, the amplitude of the swinging will be large.
For an RLC circuit driven with voltage of amplitude Vm and frequency omega, we found that the current amplitude is given by Im equal to Vm by Z, and that's equal to Vm by root of R square plus Xc minus XL the whole square, with Xc equal to 1 by omega C and XL equal to omega S. So if omega is varied, then at a particular frequency, omega naught, Xc will be equal to XL, and the impedance will be minimum. That means Z will be equal to root of R square plus 0 square will be equal to R. This frequency is called the resonant frequency. So XL will be equal to Xc, and that will be given by 1 by omega naught C equal to omega naught L, or omega naught will be equal to 1 by root of LC. So at resonant frequency, the current amplitude is maximum, which means Im will be equal to Vm by R. So the figure 7.16 shows the variation of Im with omega in a RLC series circuit with L equal to 1 millihenry and C equal to 1 nanofarad for two values of R, where in the first case R will be equal to 100 ohms and in the second case R will be equal to 200 ohms. For the source applied, Vm will be equal to 100 volts. Omega naught for this case will be 1 by root LC, and that will be equal to 1 into 10 power 6 radian per second. We see that the current amplitude is maximum at the resonant frequency. Since Im will be equal to Vm by R at resonance, the current amplitude for the first case is twice to that for the second case. Resonant circuits have a variety of applications, for example, in the tuning mechanism of a radio or a TV set. The antenna of the radio accepts signals from many broadcasting stations. The signals picked up in the antenna acts as a source in the tuning circuit of the radio, so the circuit can be driven at many frequencies. But to hear one particular radio station, we tune the radio. In tuning, we vary the capacitance of the capacitor in the tuning circuit such that the resonant frequency of the circuit becomes nearly equal to the frequency of the radio signal received. When this happens, the amplitude of the current with the frequency of the signal of the particular radio station in the circuit is maximum. It is important to note that resonance phenomenon is exhibited by the circuit only if both L and C are present in the circuit. Only then do the voltages across L and C cancel each other, because both of them will be out of phase with each other, and the current amplitude is given by Vm by R, the total source voltage appearing across R. This means that we cannot have resonance in a RL or RC circuit. Power in a AC circuit, the power factor. We have seen that a voltage V equal to Vm sin omega t applied to a series RLC circuit drives a current in the circuit given by I equal to Im sin omega t plus phi, where Im is given by Vm by Z, and that will be equal to tan inverse of Xc by Xc minus XL by R. Therefore, the instantaneous power P supplied by the source is given by the equation 7.29. The average power over a cycle is given by the average of the two terms in RHS of the equation 7.29. It is only the second term which is time dependent. Its average is 0, positive half of the equation cancels the negative half. So the equation can be written as P equal to Vm Im by 2 cos phi, and that will be equal to Vm by root 2 into Im by root 2 cos phi. That is given by Vi cos phi. This can also be written as P equal to I square Z cos phi. So the average power dissipated depends not only on the voltage and current but also on the cosine of the phase angle phi between them. The quantity cos phi is called the power factor. Now we will discuss the following cases. The first case being the resistive circuit. That means if we have only a resistance in the circuit. If the circuit contains only pure R, it is called resistive. In that case, phi will be equal to 0, so cos phi will be equal to 1. That means there is maximum power dissipation. The second case, which will have only inductance or capacitance. If the circuit contains only an inductor or a capacitor, we know that the phase difference between voltage and current is pi by 2. Therefore, cos phi equal to 0 and no power is dissipated even though a current is flowing in the circuit. This current is sometimes referred to as wattless current. The third case, we will have all the three components, that means inductance, capacitance and resistance. That means it is called as LCR series circuit. In an LCR series circuit, power dissipated is given by the equation 7.30, where phi equal to tan inverse of Xc minus XL by R. So phi may be not zero in RL or RC or RCL circuit. Even in such cases, power is dissipated only in the resistor. The next case, the power dissipated at resonance in LCR circuit. At resonance, Xc minus XL equal to 0 and phi equal to 0. Therefore, cos phi will be equal to 1 and P equal to I square Z, that is I square R. That is maximum power is dissipated in a circuit through the resistance at resonance.
Transformers. For many purposes, it is necessary to change, or transform, an alternating voltage from one to another of greater or smaller value. This is done with a device called transformer using the principle of mutual induction. A transformer consists of two sets of coils, insulated from each other. They are wound on a soft iron core, either one on top of the other as in figure 7.16a, or on separate limbs of the core as in figure 7.16b. One of the coils, called the primary coil, has NP turns. The other coil is called the secondary coil, it has NS turns. Often the primary coil is the input coil and the secondary coil is the output coil of the transformer. When an alternating voltage is applied to the primary, the resulting current produces an alternating magnetic flux which links the secondary and induces an EMF in it. The value of this EMF depends on the number of turns in the secondary. We consider an ideal transformer in which the primary has negligible resistance and all the flux in the core links both primary and secondary windings. Let phi be the flux in each turn in the core at time t due to current in the primary when a voltage Vp is applied to it. Then the induced EMF or voltage epsilon s in the secondary with ns turns is given by the equation 7.31. The alternating flux phi also induces an EMF, called back EMF, in the primary. This is given by the equation 7.32. But epsilon p equals Vp. If this were not so, the primary current would be infinite since the primary has zero resistance, as assumed. If the secondary is an open circuit or the current taken from it is small, then to a good approximation epsilon s equals Vs, where Vs is the voltage across the secondary.
Therefore, equations 7.31 and 7.32 can be written as Vs equal to minus Ns d phi by dt or Vp equal to minus Np d phi by dt. So from the equation 7.31 and 7.32a, we have Vs by Vp equal to Ns by Np. This is the voltage across the secondary and Vs and voltage across the primary is Vp. Similarly, Ns is the number of turns in the secondary and Np is the number of turns in the primary. Note that the above relation has been obtained using three assumptions. The first one, the primary resistance and current are small. The same flux links both the primary and the secondary as very little flux escapes from the core. And the third one is the secondary current is small. If the transformer is assumed to be 100% efficient, no energy losses. That means the power input is equal to the power output. That means that is because since P equal to IV. So IPVP equal to ISVS. That means the product of the voltage and current in the primary coil will be equal to the product of the current and the voltage in the secondary coil. Although some energy is always lost, this is a good approximation since a well-designed transformer may have an efficiency of more than 95%. Combining the equations 7.33 and 7.34, we will have IP by IS equal to Vs by Vp and this equal to Ns by Np. Since I and V both oscillate with the same frequency as the source, the equation 7.35 also gives the ratio of the amplitudes or RMS values of the corresponding quantities. Now we can see how a transformer affects the voltage and current. We have Vs equal to Ns by Np into Vp and Is equal to Np by Ns into Ip. That is, if the secondary coil has a greater number of turns than the primary, that means Ns is greater than Np, the voltage is stepped up. That is, Vs is greater than Vp. So this type of arrangement is called a step-up transformer. which is used in the case of television. However, in this arrangement, there is less current in the secondary than in the primary. That is, NP by NS is less than 1 and IS is greater than IP. For example, if the primary coil of a transformer has 100 turns and the secondary has 200 turns, NS by NP equal to 2. And similarly, NP by NS will be equal to half. Thus, a 220 volt input at 10 ampere will step up to 440 volt output at 5 ampere. If the secondary coil has less turns than the primary, that means NS is less than NP, we have a step-down transformer. In this case, Vs is less than Vp and Is is greater than Ip. That is, the voltage is stepped down or reduced and the current is increased. This is what happens in the case of adapter, which will transform 230 volts to the desired output voltage such as 5 volts, 6 volts like that, or 9 volts like that. So the equations obtained above apply to ideal transformers without any energy losses. But in actual transformers, small energy losses do occur due to the following reasons.
Transformers are capable of receiving AC power at one voltage and delivering it at another voltage. In this way, they help achieve better transmission efficiency while transferring the power over longer distances. In this video, we will go through the working and construction of a three-phase transformer by starting from its simplest form. The basic working principle of a transformer is simple: electromagnetic induction. According to this principle, a varying magnetic flux associated with a loop will induce an electromotive force across it. Such a fluctuating magnetic field can easily be produced by a coil and an alternating EMF system. A current-carrying conductor produces a magnetic field around it. The magnetic field produced by a coil will be as shown in the figure. With the fluctuating nature of the alternating current, the magnetic field associated with the coil will also fluctuate. This magnetic flux can be effectively linked to a secondary winding with the help of a core made up of ferromagnetic material. This fluctuating magnetic field will induce an EMF in the secondary coils due to electromagnetic induction. Since the turns are arranged in a series, the net EMF induced across the winding will be the sum of the individual EMFs induced in each turn. Since the same magnetic flux is passing through the primary and secondary coils, the EMF per turn for both the primary and secondary coils will be the same. The EMF per turn for the primary coil is related to the applied input voltage as shown. As a result, the induced EMF at the secondary coil is expressed as follows. This simply means that with fewer turns in the secondary than in primary, one can lower the voltage. For the reverse case, one can increase the voltage. But since energy is conserved, the primary and secondary currents have to obey the following relationship. Three-phase transformers use three such single-phase transformers.
1. Flux leakage. There is always some flux leakage. That is, not all of the flux due to primary passes through the secondary due to poor design of the core or the air gaps in the core. It can be reduced by winding the primary and secondary coils one over the other. 2. Resistance of the windings. The wire used for the windings has some resistance and so energy is lost due to heat produced in the wire, I2R. In high current, low voltage windings, these are minimized by using thick wire. 3. Eddy currents. The alternating magnetic flux induces eddy currents in the iron core and causes heating. The effect is reduced by using a laminated core. 4. Hysteresis. The magnetization of the core is repeatedly reversed by the alternating magnetic field. The resulting expenditure of energy in the core appears as heat and is kept to a minimum by using a magnetic material which has a low hysteresis loss. The large-scale transmission and distribution of electrical energy over long distances is done with the use of transformers. The voltage output of the generator is stepped up, so that current is reduced and consequently, the I2R loss is cut down. It is then transmitted over long distances to an area substation near the consumers. There the voltage is stepped down. It is further stepped down at distributing substations and utility poles before a power supply of 240 volts reaches our homes.